Trailers for people to come in. You guys, have you ever guys thought about why the front row chairs are never occupied? Only on this side I see occupied, but has it ever happened that in any presentation or meeting, for a bigger shot, you will have more people coming in? Okay, that makes sense. Or a little more intelligent presentations, you might have more people filling in the front. Okay. Oh, is it? Okay, that's a good excuse. I like that. I like that. We used to be creative when we were in college too about why you're sitting in the back benches. Yeah, sir, I think you're so loud. I think we can hear better at the back, not in the front. Yeah, we used to be creative too. Okay, so 3:04. Let's start. The same conundrum like yesterday. I don't want to be punishing you guys just because you came on time by keeping you wait. One more session today. Thank you very much for coming. We'll try to talk about smart cities and AI. Like I promised yesterday, I will not be getting into the finer details of implementing some of the AI solutions for the smart city situations, but I'll talk about what's happening in the smart city world and talk about some of the AI implementations. I'll share some of the papers that's been published in the last 2-3 years. But smart city is one of the most exciting topic I've been hearing from many sections, and of course including Hexagon. Hexagon, we do have SI and safe city concept being implemented. It will not be too far away from today that you'll all will be implementing some variation of smart city or a safe city application in AI. So have you guys figured out whether you are going to be an AI engineer or not yet? I know the managers are going to get upset when I say that, but I think if you really want to become an AI engineer, I think it's time is now. But we're going to talk about smart cities today. The most common thing can be the traffic or the parking issues or any crime prevention, crime detection. Those are some of the very common smart cities or safe city use cases. But there are other use cases too. I just intentionally picked some not so commonly heard use cases just to drive home the aspect of the diversity of use cases you have in smart cities. And there are many companies working on smart city solutions. Even companies like Google and Baidu are implemented a bunch of smart city projects. I think it's Baidu or Alibaba, I think, has implemented a couple of smart city implementations in Asia, which have been really acclaimed. So you may want to read about that. This is an example of which restaurants need to be inspected. This is, I think, an example from United States, but I guess this could be implemented in Hyderabad too. I think that we have so many restaurants and there's a need for the inspections by the health inspectors to check the restaurants. Here, identifying which restaurants need more inspections compared to the other restaurants. And if you look into the machine learning features, there are only 11 features are being used to identify which restaurants need more inspections. Similarly, I think for land use classification, are you using land for cultivation or otherwise, if you have any flood situation or a fire situation in a jungle, you can actually do a classification of the lands. But this one is an example of Ho Chi Minh City in Vietnam, where AI model is being used to classify the land. Clean streets is another implementation example of smart city where you can figure out which streets are not clean, and of course, as I mentioned earlier, you can find more information using these links at the bottom. One very exciting problem statement I found is gunshot detection. You can use a video processing solution to identify a crime that's happening at that moment. But many times, if the video may not help, especially if the cameras are not in the line of sight, or if it's dark and hence you cannot get a real clear image, the image processing models in artificial intelligence will not work. In those situations, you can have just regular sensors, in this case, audio sensors, capturing the sound and then detecting if the model heard a gunshot. But here is an interesting situation. if the gunshot happens to be in a very crowded place or very noisy place, you would have the model receiving a bunch of noisy signal too along with the gunshot sounds, and hence model has to be extremely intelligent enough or generic enough or generalized enough to figure out what's happening in the sound, and then the rest all is a basic software implementation of localizing and identification of the location where the sensor is, and hence where the sound is coming from, and hence where the crime is happening. There's another example of a city in the United States called New Orleans, trying to find out the risk of smoke. And New Orleans is a city which actually is quite an old city with lots of wooden constructions, and you have the restaurants and the houses very close to each other. There's a possibility of fire risk. And the city of New Orleans is constantly mapping to find out which areas are prone for higher fire risks. And this could be predominantly just because of the wooden constructions on the cooking part, but also it could be based on the heat, the temperature outside. And another smart city implementation is just the AR part of, if you are in a new location or a strange location, you want to find out the information about what you're seeing, you can actually hold up your cell phone to find out the various items or objects you're seeing in your screen. I'll give a couple of seconds, read some of these use cases. There are so many, I could just capture more use cases, but there's lots and lots of use cases. And I'm actually going to be talking about only some of those use cases which are here in bold. For example, detecting human action using videos or face recognition and vehicle count maybe. Yeah. But if you want to talk about any other use case, I can quickly explain what it means. Okay, let's move on. Before I get into the actual use case implementation, I want to talk about if you want to make it as a production system, where in a city you want to implement a smart city solution, you have to look into the architecture of various things. For example, the online processing of data, the infrastructure you're going to be setting up in the city to collect the data, to process the data, to clean the data. And here is an example of the online data processing architecture where, of course, published in a paper in 2017, September. It talks about what type of data sources you have that's coming in, the data that's giving the data, and then you talk about the various types of systems that would be processing the data. And if you look into the complexity of the context diagrams here and here and here, the online processing of the data is going to be really complicated. And the reason for that is just the sheer amount of data that's coming in. If you have sensors on the street lights, sensors on the cars, on any other types of vehicles, and sensors on the human beings, all of them generating data and being shared, it's going to be an extra complication. Text processing. I have an example. Let's say there is a crime that's happening on a specific street, or let's say a procession going on in a street, and the city government has not received any official information about whether it's a traffic accident or a crime or a procession happening. If you want to find out from the crowdsourced information of, let's say, individuals are taking pictures or videos and uploading onto their respective Facebook accounts or other social media accounts, how would you find out what's happening in that? And can the city proactively tap into this publicly available information to find out an event happening? If you have the videos being posted or pictures or videos, you can have video processing models that focus on that. But if you have just texting, people are sharing information using text, you can use a bunch of natural language processing activities to identify the right information, process a few models. I'll not talk about the models today. We talked about text summarization a couple of days ago, and where I talked about various neural networks that you can use to look into the text, convert the text into vectors, and process the text to make sense out of the information. But in this case, as a safe city implementation, you can look at the stream of social media stream of text that's coming in. You can process, identify whether you're looking for a crime or a procession or a traffic jam or any other event or a flood. You can look at that information and have the model identify what's happening and then send you the alerts. I mentioned about the infrastructure need. If you can only imagine about automobiles having sensors and they talking to each other and forming a very safe network, the number of cars available on the street and the amount of data that they're sending across into a central server, just imagining only about the cars, will be running into lots and lots of data. But if you add other types of sensors generating the data, the amount of data that's coming in and the diversity of technology you're going to be using to capture the data. For example, if you have a wristwatch as a data creator and sending the data across, you have your mobile devices, you have your laptops, you have automobiles creating data. This would be the architecture I would recommend as part of the paper again in 2017. If you have the traffic lights and the vehicles and individuals, human beings communicating the data, you should have basically two types of information streams. You have the data stream that's coming in, which you process immediately to find out something which is a real-time information that you want, and some other information you keep on the side which you can process as a batch maybe later on for future evaluation. But at the same time, you can make available certain APIs for third-party organizations. Let's say if you want a Google-like company finding out the traffic conditions in a certain situation, but if you have a smart city which has implemented the smart city solution and collecting the data of vehicles, that information could be provided to all the cars or other third-party companies which are looking for traffic information. The sensor data, even though it's huge in size, you maybe for a second imagine that you can manage the data, but when you talk about cameras in various locations, in a city of, let's say, 1 million to 5 million people, you can imagine anywhere between 10,000 to 100,000 cameras located. So every 1 hour, you actually have 10,000 hours of video that's being captured and being sent across to be stored in central servers. For that amount of data, having models process it even at the central location, or if you think of edge computing where you can have some other processing of the video happening on the surveillance camera itself, but still the amount of data that's coming in is huge. This is I think 2015, actually it's 2017 paper, but it's talking about how do you manage large amount of video data that's coming in. There's one area of solution that's been proposed, I think, in the last 2 or 3 years. It's called two-stream video processing, where the optical movement of the objects in the video could be evaluated by one network, and the other network can look at various frames of the video to do an action classification. Let's say there's a car moving and it involves an accident. You have one neural network processing the frame by frame to identify how the optical movement of the objects happening in the video, and the other neural network can process the action classification of the actions in the frames. I remember reading 6 months ago, I think it was Walmart, which wanted to find out what will be the revenue impact in the next few quarters based on factors which are not right now under their control. In other words, they do have a supply chain, they do have the number of customers that's walking in, they do have information about number of people buying various products and the credit card swipes, but they said, okay, can we look at any other method of predicting independently what will be my revenue going forward for the next 1 or 2 quarters? They came out with this interesting idea that, okay, can we take a picture of the parking lots of all the stores, evaluate the parking lots to see how many cars that's coming in, what type of cars they are, how long a car is parked, and whether it's a minivan versus a two-door car or a four-door sedan, and then looking at even sometimes the colors of the car, predicting what type of people coming in. And the model was developed to extrapolate, finding out what will be the revenue for the next 1 quarter or the 2 quarters. And that would be a combined revenue for all the stores put together, or it could be per store information too. And they wanted to compare that information with the other supply chain information to see, is there a match? And in that process, they actually used this method of taking an aerial view of a parking lot to identify the number of cars. This is the convolutional neural network architecture which they've used. But the interesting part is here, when you take an aerial view, let's say of 10,000 feet or even 20,000 feet away, the number of pixels that represent the cars will be so few, model will have too much of a problem in identifying the number of cars. But still, they actually could implement a model to identify the cars and even the colors and how long they were staying. And they also used something called YOLO. Have you heard of YOLO? What YOLO stands for? You only live once, not the other one you thought about. YOLO 1 was a model that was implemented, I think, almost a couple of years ago. YOLO 2 came, and now YOLO 3. YOLO 1, 2, 3 models are high-speed image processing models that can look at a scene or a situation and can detect a few of the objects in the screen. For example, if you're using that on a moving vehicle for an autonomous car, it can actually identify pedestrians, other cars, roads and trees and all of these things. YOLO became very popular, especially in the autonomous cars too, for the efficiency, accuracy and the speed of computation. YOLO 2 actually came out with 224 frames per second. So it actually can literally do real-time processing when you're driving the car, especially in a country like the United States with 60 miles or 70 miles an hour, it would be fast enough to detect. YOLO 1 was, I think, only 42 frames per second. YOLO 3 is more of a lot more efficient, less number of parameters it uses, less number of compute power, but it's almost the same number of frames per second. So you can use YOLO 2 to identify various objects, but this one actually has a different architecture. We talked about image processing yesterday, and I explained to you how a typical convolutional neural network works, and this is the architecture here for this specific example of counting the number of cars in the parking lot. I intentionally picked one solution which may not necessarily be an artificial intelligence solution or may not be using all the modern cameras and stuff. Here the model uses the radio signals. Detecting the traffic flow. On a street, if you want to find the number of cars that's going in and what type of cars too, you can find not just the traffic, the congestion part of it, but also you can find out what will be the life of the road you have laid, and then you can consequently see how we can improve the road layout. It's 22 minutes into the presentation. I see a few people yawning. Could we all stand up and stand there for a minute? I know some of the people who don't want to physically are not capable of standing for too long. They can keep sitting, but it'll be an interesting experience. I'm actually doing this exercise, and today being the last day, I will take the liberty that if even after standing, if you're yawning, we'll do something else too. But bear with me. After lunch, I know it's going to be difficult, and this is not an exciting topic for some of the people. So let's see if you can come out of your slumber while we're talking. So in this example, if you want, this is Jan of 2018. There were 6 different sensors placed on a road, 3 sensors on each side, to detect when a vehicle moves in. It's not just the obstruction of the signal that's coming in, but the model can also understand based on the duration of the obstruction and also the disturbance of the signal on what type of car it is. Actually, it's a very spectacular implementation which had a high accuracy rate to detect whether it's a a small car or a big car or a big truck or a minivan sort of thing. Again, for implementation details, you can always read the paper, but this was a very exciting paper I found, which I thought I should share with you. Though not being used for any, we didn't use any, they didn't use any neural networks, but it was a good solution for smart cities. Another interesting scenario I found is a taxi demand. There are some papers published by Uber and Lyft, but I picked up this, which is not from any specific taxi company, about how to predict the demand of for taxis. Please sit down. I feel a little awkward. Yeah. Hopefully from tomorrow you'll not have the torture because we don't have any more sessions. But if you guys have any suggestions on how to avoid yawning after lunch, I'll be happy to hear. Even to the extent of, okay, why not we have lunch after 3 p.m., but I don't think that will work. I'll pick a different model to explain. In image processing, we talked about yesterday, if you want to detect an image, detect an object in an image, you can do the regular training on the convolutional neural network. But in a smart city solution, let's say you have a surveillance camera watching the traffic or watching the people, you want to only watch for certain important activities. For example, you can train a model that only responds to a traffic accident, or you can train a model only responds to detecting people of interest. You really want to ignore the rest of the people, but you want to pick only such people. So identifying a salient features in the video which you want to capture, you can train it. Here is an interesting solution where you have a picture with multiple objects in the image. For example, you have human beings, you have a big, I think, airplane there, and then maybe the walls and the windows and people, other people walking too. But you want to find out, let's say, the number of people in the arena, or the number of the cars that's going in. So the salient feature will be identifying only the cars and the number of cars, or only the people and the number of people, or only men or only women, whatever information you want to capture, the salient features. This makes it a little more easier to train the CNN model, where the amount of data I think is lesser, but the technique you use is called segmentation. You actually have you do pixel level segmentation, or even just the object segmentation too. But this is the implementation of that here. Okay. Of all the smart city solutions, the two most difficult use cases are identifying a human being and identifying a vehicle. Why is it difficult to identify a human being? For example, if you go to Facebook and if you upload a picture, the model immediately finds out, oh, this picture where you are and with your friends are, it identifies the names of your friends. The reason why the model recognizes those pictures easily is because it's a controlled environment where the model has seen already the face in your picture, because they're all your friends and it's somewhere in Facebook, and it picks up and then automatically tags them. Sometimes it cannot tag if the picture is not clear, or if the person doesn't exist in your Facebook network and the model is not able to figure out, but it's very easy. But in a city situation, here is the complexity. If you have 1 million people in a city or 10 million people in a city, you can't actually have pictures of all people taken. That's not democracy. So you will not be taking pictures of people. Number two, in Facebook-like model where you have the image processing model which is detecting the human faces, you actually have very clear pictures being presented to the model, because you want to have nice pictures, clear pictures of you taken and then uploaded to the model. But in a city situation, you have the cameras typically around 5 feet or 10 feet up the ground, and hence the view is always at an angle, number one. Number two, you will not have very high definition cameras all the time. Some places, maybe in the airports, which is a sensitive area, you may have high definition cameras, but not every in a city. Next is the lighting conditions. Sometimes the lighting conditions are not ideal. Because of all of these reasons and a few other reasons too. For example, the other reason could be the line of sight. If the person you want to watch, he's not in the sight of the camera, you'll not be able to get a real good picture. But on top of all of this, the real complication is if you've never seen the person and the picture is really, really blurred, and if the question is the person I saw on camera 1 on a Monday morning 9 a.m. the same person I see on camera number 10 on a Tuesday, let's say 7 p.m. There are 2 different days, 2 different locations, 2 different cameras. The person would have maybe changed the dress, looks different, maybe different haircut. With all of these complexities, identifying a human being correctly is the most difficult part. In this case, I will explain how they have done it, but before I explain this, let me recollect how image processing is done. We talked about that yesterday. You have the convolutional neural network, you have an image, you give as an input, and then you do a training, you have the ground truth of the label and do a back propagation, and all of these things, nice things happen. Now, if you have the right image and you have a nice label for that, before this paper came, for a similar paper published I think a few months before for person identification, they used, while training, something called triplicate loss. You have an image, you have the image of the same person at a different time and hence different view, and then you have a third image which is entirely different person. And you give these 3 as an input to the model, telling that for the first picture, second picture is the same person, even though it's a different picture in different time and different lighting conditions, and the third picture is a wrong person. If you keep on doing that process, let's say a few 100,000 times or even 1,000,000 times, model would get heuristics or become intelligent enough that if I see one picture, I know how to pick another picture from maybe a million pictures which matches with the picture in this person in this picture, and also knows it should not be like the other person, the third picture. So in other words, you do a triplicate loss. You have an objective statement which you create which will look at matching 1 and 2 but not 3, and that's called a triplicate loss. And in Jan of 2018, they came out with a newer model. It's a conference called CVPR. They presented 4-level quadruplet loss, which just an extension of the existing idea, but they actually got better accuracies. But the actual implementation is very similar to what I explained to you, but most probably I'll pick this paper when I come back, I think in August, September, where I'll go into the complete implementation of it, of a single paper, including the code and other stuff. Another paper which works on the same use case of identifying the similar faces. You have a closed set and an open set, and closed set is an example I talked about earlier in a Facebook environment where the model has seen the photo and has the identification of the person at least once. And that's a closed set. The model has seen once, and hence when you supply a new photo, it can immediately detect. For example, if you have in a criminal situation, you have a second-time convict. When you capture, you give the picture of that person to the model. Model can immediately detect because the model has seen that convict's picture earlier and hence can easily detect. So in some of the safe city implementations, you can still use a controlled set implementation or a closed set implementation. An open set implementation is what I just now explained, where the model has never seen the first image or the second image or the third image, and then you actually do a triplicate loss and do a training. This actually, they use, in this sphere face model, the embeddings, the vectorization of the image was done differently. And I'll explain that maybe next time when I talk about what it is. Here is a comparison of their paper in terms of accuracies compared to so many other papers that's being published. Now, the reason I picked up this paper and also the number of solutions here is there are so many implementations of image processing that's happening, and these are all, I think, published in 2017 and 2018. Okay, let's talk about another type of use cases is looking at a video and detecting action. I talked about two-stream processing. This is the paper I was referring to when I say you have a video that's happening. Let's say someone is running, there's an accident, or someone is lying on the street, or if you want to find out what is happening based on a video, not based on a still image, then you need to study multiple frames, and over a period of multiple frames you can find out what is the action that's happening. So you have two streams of convolutional neural network, and one stream would study the optical flow of the images. For example, if you have a car that's running on the street, in the spatial stream CNN, you would find out that the model will find out the car is actually moving from left to right, from A to B. So it actually feels, it says there's a car moving, and then in MotionNet, it actually does a classification of whatever action you have defined. For example, it's running fast, or it's running slow, or it's stopped, whatever is the classification action you have defined, the second model will figure out. So this paper, I think, came early 2017, was kind of revolutionary of using two neural network architectures that will process the same video and looks at two different aspects of the video. One is the optical flow, and the other one is the action classification, and combining that information. It's more like an end-to-end training. I explained what the end-to-end training term means. It's an end-to-end training of a single architecture of two different CNN architectures, and really came out with higher accuracy. If you look into the architecture of the top stream, and this is the architecture of the bottom stream, and I mentioned to you yesterday too, typically in convolutional neural networks nowadays you have convolutional layers and pooling layers. It's a mix and match of so many, and then towards the end you have a fully connected layer with a softmax on that. This was a use case where I've heard many cities are looking for, based on videos either picked up by surveillance cameras of the city governments or videos posted on Facebook. Can you find out similar activities happen in a certain location, and then classify all of those activities together? For example, there's a procession happening, or there's a crime happening. So which I explained earlier, and here is the paper again published in middle of 2017. But this is the same thing where you look at the video, you look at the optical flow, and you also look at the action classification on two different streams and identify overall what's happening. That's all I had today. In the smart city implementations, which you may see more and more in Hexagon, whether it's using classical machine learning solutions or deep learning solutions for, let's say, audio signal capture or an image capture or a video capture, would be more and more use cases that will be implemented in Hexagon. And I myself already met with a couple of divisions, and they want to really use the geospatial images of, let's say, of a forest or a land and make sense out of it. In safety cities implementations, they want to take an image of a location to identify the traffic or the parking lot situation, and metrology, the machine intelligence division, I think, is also looking for a similar implementation. Mining and agriculture are two divisions which are about to meet. They do have similar artificial intelligence solutions requirements for using the spatial images. That's all from me for today. Questions? Yes. The question is, when we get the data from various sources, how do you know the data is genuine? That is a big problem, and especially if you have multiple types of sensors that's contributing for the data. Many times the sensors are corrupted, some sensors are down, or sometimes they are older generation sensors sending the data, but that's not being captured by the new system. There's so many variety of possibilities that the data being wrong. There are some techniques. For example, you can figure out what data is right or wrong, and then you can eliminate some of the data. As a data scientist, you will start looking at the data to figure out what information that need to be kept and processed. I can't give a specific answer, but predominantly you start looking at which data to be consumed and which data should not be consumed. Many times, if you have, let's say, a video data that's coming in, you may use two different video streams from two different cameras to verify whether you're getting the right data or not, because the model which is looking at one data stream may predict, oh, there's a crime happening. The model can look at another video almost of the same location, may predict it's nothing is happening, and then a human intervention may be required. But right now, people are struggling with just processing the data itself, and there are more issues about the genuinity of the data, how genuine the data is. Yes, sir.
Yeah, recently there have been some incidents in Hyderabad, like kidnap or something, where the police have tracked the time at which the culprit is running with a car or something, based on the time, and then they have the knowledge of where the person might go, like the routes, the directions, and then identified the other possible places where the video cameras were installed, and then based on the time it takes for the person from here to there, they quickly went to that location and identified, and they scanned through that half an hour, 1 hour video. So when we look at identifying people or objects, do we have that maturity in the solutions, whatever that we are talking about in the papers, that it will take into consideration the possible routes, the possible timelines, and identify the possible match?
Let me understand the question. Okay. In the scenario what you explained, having a model predicting where all the culprits would have gone or where they would have hidden the kidnapped person, I haven't heard of papers being published, but with my basic machine learning experience, I know we can develop the model if we have the data, but I'm sure it's going to be a difficult data to get. But we don't even need to go to that scenario, because if you have the surveillance cameras, enough surveillance cameras, I don't know how many enough means, but enough cameras, you would be able to identify if someone is missing, and if that person is caught in any camera, it can immediately detect what it is. But I guess that's not your question. Your question is, if an event has happened at location XY,
Yeah.
Can I know where that person has gone after time t, whether it's x1, y1 or x2, y2? Theoretically, I think it's possible, but I have not heard of any problem solutions being done in that regard.
And just in continuation with that, like if you have to have a practical significance of AI in security scenario, if you can help the police to track this person instead of manually checking through days and days of videos, this will be really helpful. And in terms of like practical things, like how much data power is needed in the back end to process this kind of information in the thousands of the cameras that we will have within the city, and how much time is it going to take, like 1 hour, 1 day? Any thoughts on the processing power?
Right now, if you have, let's say, Alibaba implemented in I think Malaysian city, I forgot the name of the city, but they've implemented in Malaysian city for a smart city implementation, where they do have, I guess around 10,000 or multiples of 10,000 cameras, video cameras, which is capturing the data. What they've done is, they've done a couple of techniques to eliminate unnecessary data. For example, there is a small scale image processing model sitting on the surveillance camera. It's looking at the video. If there is no special event that happens, it would not capture the data. It would just discard the information. It keeps, of course, nevertheless, for the last 1 hour or 2 hours, X number of hours, and after that it just discards it. But if a salient event or an important event that's happening right at that moment, it captures the data maybe X minutes before and X minutes after and sends it to for further processing. But the model already alerts. It knows there's an event that's happening and I found an interesting data. So you have a different image processing model maybe sitting on the cloud which is getting this data and then quickly process it. Many times the response time is like in a few minutes, it doesn't take too much time. But let's say you want to study the patterns of the traffic that's happening on this road on a daily basis or an hourly basis or a monthly basis, then you would actually capture lots of data, do an offline processing, which is not a live real-time requirement. For the real-time, one technique is have part of the processing done at the edge device itself. Second is sometimes if you have the accuracy rates lower, let's say 40% accuracy, 50% accuracy, but the response time is very, very high, people don't mind doing it because you want to err on the side of, let's say, being extra cautious. So even if even there's no one is kidnapped, but you want to quickly respond to something's happening, maybe that's a good thing. But the downside of that is misuse of the resources. Let's say the model is making all the time wrong predictions and you have cops running in different directions of the city, and then it's a waste of resources too. So that's the balance that they're trying to find. But the safe city implementation still now, especially for crime prevention, if the model predicts a dangerous situation happening, it's always in terms of minutes. The response is always in terms of minutes. Yeah.
So,
Other questions? Okay, thank you guys. Thank you very much.
one last question
Ooh.
from here.
Oh, from here, that's a good direction.
Yeah.
Yeah.
The machine only understand numbers, right? So you said it will process images based on the pixel number. So how does it understand and processes the sounds?
Songs?
Sounds.
Sounds. So that's a different area of study for signal processing, audio signal processing. There are different techniques of processing the audio signals. Every signal has an amplitude and phase. There are models which are looking only on the amplitude of the waves. Let's say you capture the sound waves, and let's say you take a time period of 10 milliseconds or 100 milliseconds. So you have inputs of 100 milliseconds of audio signal that's coming in, and you look at the amplitude information for that 100 milliseconds. So you have one number which signifies the amplitude on that time period of 100 milliseconds. It could be 10 milliseconds too. And now you're converting the entire signal into a number because you're tracking the amplitude. Or you can track the phase details of the signal. And before this audio signal is actually used for processing, you do something called pre-processing, where you eliminate the noise and you get the little more pristine signal. And for that signal, you actually start looking for either amplitude or phase or some complex way of integrating the phase and amplitude information. And eventually, in other words, you are actually converting. To summarize, you're converting the audio into a number too. And the same logic applies to, I think I mentioned in a different presentation about using Wi-Fi signals to detect human activity. Same thing, you have Wi-Fi signals that's bombarding various objects in the room, excuse me, and you're converting those signals into numbers because you actually have the routers, transmitter and receiver. You have every transmitter, every receiver has 30 subcarriers, and each of the subcarrier is transmitting a number. You look at all of those numbers and construct the message into a matrix. That's the Wi-Fi signal. But in the audio signal, you convert that to a number 2 again. Yeah. And there are newer research going on how to use not just the amplitude and phase. There is something called angle of arrival, phase change. Instead of just looking at the phase at every time, they're looking at how the phase is changing because the audio signal is coming directly from the source of the audio, and also it's bouncing off from another object, let's say bouncing off the wall, and those two signals, the same audio that's coming in, one comes with certain phase and the other one comes with a different phase, and the phase change would be also being used at to define a model. Yeah. The question is there a research going on to stop border infiltration? Well, that's more of a use case about how government of India, maybe in this case, or any government can actually stop illegal immigrants or terrorists coming inside into the border. But I guess the AI part of it can be, you can actually have a image processing solution, or you can also have any other signal processing solution where it's detecting the signals and then processing the information. For example, video does not work all the time, especially if it's dark and line of sight situation. You can also have those infrared cameras, which actually looks at even in dark times too. And you can also have, in addition, sensors which is sending constant signals and using that signal information to detect if there's any human activity. How do you do it? Then you actually have to collect the data, maybe going back to the question I answered a few minutes ago. If it's a signal, look at various signal information to see how signal changes its structure based on an intruder that's coming in versus not, and then train a model. The video processing and image processing too, that if you give a data set to the model, it figures out whether someone is coming or not. So so the AI part of it is to detect human beings, whereas the use case is how to stop the infiltration.
So in that case, how will we avoid the local minima?
Yeah, that's a little more deep question. I think the question, you got the mic only towards the later part. He said when you're doing a machine learning or a deep learning, artificial intelligence problem statement, every problem solution actually has a local minima, the global minima. How do you find out which one is the, how do you know that you're not stuck at a local minima, and how do you really go to the global minima? People have not figured out. There's lots of ways of doing it. You actually have the learning rate can be as small as possible so that you really don't get stuck, and there is something called momentum. You actually can add some momentum so that actually when it's stuck in a local minima, it can jump out of the local minima, but it doesn't take too much of a leap to land in another local minima. That's a pure mathematical question. I don't know how many of you guys are interested. Akshay, do you know the answer for that? Okay, yeah, there are a bunch of techniques available. Learning rate and momentum are one of the most common things companies have used. But even sometimes, even the way you initialize, sometimes it may just not converge. Just throw away the entire model, start another model, and this time it may converge. It's almost like you have a real valley, and you go one day for a hiking in the valley, and the next day you go from a different direction, third day you go from a different direction. One of these days you really reach fast to the bottom because you picked the right location. But no one told you there's a right path. You just found it. It's exactly the machine learning model too. Based on the initialization, based on the amount of data that's coming in, even the type of data, when you do the mixing and matching of the batches, let's say if you have 1 million data points and you actually pick data point 1 to 5 and then 6 to 10 and all of that stuff. Otherwise you mix maybe 1, 3, 5, 15 as the first batch and then mix and match. That may change your local minima thing too. And another technique is have multiple models instead of just having one model and then take an average of the solution too. But that's a huge problem even today. I don't know how many of you guys understand the local minima and global minima part, but that's a very typical machine learning problem. Or when you are trying to have the model converge to a final answer, correct answer, sometimes it may not give the correct answer because it's not able to learn, it's not able to understand correctly the problem. And that's what is called getting stuck in a local minima. And the pictorial representation of that scenario is, imagine you are going down a valley and you want to really reach the bottom of the valley, but there may be some small holes or troughs on the path. You may just get stuck there. You may not end up reaching the global minima. And as a human being, you can see where the global minima is because it's right there. But machine learning model cannot see it because it's just all random data. And in that data, to really figure out where the global minima is, I think it's difficult. And hence, it's a big problem. Yeah, convergence is a huge issue for machine learning even today. That's why models you have accuracy rate of 70%, 80%, 90%. That's all because it's getting stuck somewhere in the local minima too. Websites for more information about machine learning. I had already given a couple of links about the blogs. I think people actually can read. Maybe I think that would be a good starting point because that blog refers to a bunch of other links and there's lots of information. See, the problem is there is a lot of information, which is actually not a good idea for you guys to get exposed to so much of information because it could be just intimidating to learn that information. But the blog which I gave you, the first blog, that would be a huge starting point, and after that you can always find more information yourself, yeah. Because that blog itself refers to. But it's a good idea. I think all of you guys, if you have not read the blog, you should read that now. It's a good starting point. It's a good idea on reading on a Friday evening when you're really getting bored, you're not doing anything at home, no party is happening. I think it's a good idea to just start reading the blog. Yeah?
Why
Yeah. Oh yeah, okay.
why Python is always preferred for machine learning? I mean, as far as I read some articles on Quora and other websites, I found that Quora is slow in terms of performance wise. Is it because it provides some inbuilt libraries?
You're talking about Python language, and what is the other language you said?
Any other language?
Any other
As
language?
compared-
Yeah, okay. I think it's just a matter of, I think, the ease of learning, because it's a really structured language. I think it's maybe a scripting language too. It's very easy to learn, and that's why people are picking up. It's more modern, and many frameworks have used Python, and hence if you really were using TensorFlow or the Cafe, PyTorch, etc., you may as well learn Python also. So it's all multiple factors helping each other. It's a vicious cycle. And Python was not this popular even maybe I think 3 or 4 years ago, I guess, but it's really popular now. Maybe companies like Google, Microsoft, Kaggle, these are some of the reasons why I think Python has become really popular. It's just a okay, now this time really the final thank you. Okay, thank you very much. Yeah, thank you for your time. Thank you.